Hey everybody. This week we are going to be starting a new function called exponential functions. We're moving to what the inverse of an exponential function is, and that's a logarithmic function. And we'll learn how to solve equations, graph them, talk about transformations, and all of that good things. So here we go. Exponential functions. When the base is a constant and the exponent is the independent variable, then it's an exponential function. And I have an example here. This y is the same as our f of x or g of x. It's just in function notation. So y equals ab to the x. This b number here must be a number that's positive, and it has to be something other than 1. So now our x is the exponent, which is why it's called an exponential function. So we're going to be looking at growth and decay. And this little note down here, it says a positive real number other than 1. Think about for a minute, why must this number here be something other than 1? What would happen if that number was 1? So in this video, I'm going to be toggling back and forth between this screen and Desmo's screen so we can take a look at some graphs. So I've already graphed some graphs in Desmos. So here's some functions here. The one in the red is exponential growth, and the one in the blue is exponential decay. Keep in mind you read from left to right. So the one in the red is rising from left to right, so it's going up. And the one in the blue is going down from left to right, so it's going down. So again, the one in the red is exponential growth, it's rising, it's increasing. And the one in the blue is exponential decay, so it's falling and going down. Let's talk about what the domain and the range for this function is. So my domain is going to be all real numbers for both. So the blue and the red, the growth and the decay. My domain is all real numbers. Now let's talk about what the range is. The range, it looks like the blue and the red are both going to hit the x-axis where my little pointer here is moving. And the same thing on the red, it looks like it's going to reach the x-axis, but it's actually not going to touch the x-axis. It's just going to get closer and closer and closer and closer, but it's actually never going to hit the number 0. So if I use my points here, look at your y value. It's 0.287, 0.222, 0.114. It's going to get smaller and smaller and smaller, but it's never actually going to be 0. So my range is anything greater than 0. So again, my domain and range for both of these is the same. Domain is all real numbers, and the range is y is greater than 0. It cannot be equal to 0, so make sure we put that it's just greater than 0. And the reason for that is because it has an asymptote. An asymptote is a line that my graph touches, but it'll never actually approach. So you want to write this definition down and pause it if need be. So exponential functions have asymptotes, meaning it has a line that the graph will get closer and closer and closer to, but never touch. Think back to what I was just doing on Desmos, how the y value was getting smaller and smaller and smaller, but it will never be 0. So there'll be some line that this type of function gets close to, but never touches. So that is called an asymptote. Now, I want to take a look at a couple of more functions. We're going to go through, we're going to state the domain and the range. That way you can have hopefully a better understanding about this idea of an asymptote. So these are the two functions that we're going to do. We're going to do these two functions here. So in Desmos, we're going to graph these. Okay. So the first one was f of x equals 4 to the x power plus 2. And let me cut these two off. All right, so if I'm looking at this function here, f of x equals 4 to the x plus 2. Again, for all exponential functions, your domain is going to be all real numbers. So for all exponential functions, my domain is all real numbers. The range is going to be what changes from problem to problem. So where my pointer here is moving, notice it's getting closer and closer to, let me see if I can highlight that a little better for you. Let me erase this here. Okay, so there's like a line that is getting close to, and that's off a little bit. So there's a line that my graph is getting close to, and it's a little crooked here, my apologies. But it's getting closer and closer to this horizontal line that I'm drawing in. And this horizontal line is the number 2. And I also can see the number 2 from over here in my function. So I can see that positive 2 there. So your range is getting closer and closer to the number 2, but it'll never be the number 2. So my range is going to be everything that's greater than the number 2. So when you write your answer down for this particular function, my domain, it goes from negative infinity to infinity, which is all real numbers, but my range is going to be greater than the number 2. It'll never be 2. It'll be 1.9, 1.999. It'll get closer and closer to the number 2, but because there's an asymptote there, it'll never actually approach the number. It'll never actually be the number 2. It'll approach it, but it'll never be that. Let's try one more. So I'm gonna come over here to Desmos and type in the second one that's there. So this time we're typing in f of x equals, and we're taking a look at 1/3, 3 to the x power. And we're going to state what the domain and the range is. For all exponential functions, your domain is all real numbers. So we can go ahead and put negative infinity to infinity. Our range is what changes from problem to problem. Again, this purple is getting closer and closer and closer to the number 0. Let's actually take a look at some numbers. Notice it's 5.17. The y is 2.28. Then it moves to 0.17, 0.00, and it gets closer and closer and closer and closer, but it'll never actually be the number 0 because there's a line that it's going to approach, but it never touches. So my range for this particular function is going to be greater than 0. Again, if you want to write these in set notation, I know some of you guys like to write it that way. This would be from 2 to infinity. And then this one would be from 0 to infinity. So depending on how you like to write it. So domain for all of these functions
Good morning, and pardon the interruption.
Goes from...
Well, if you have fourth period planning, you will do your PLC at 12:15 today. They're going to go ahead and combine third and fourth period.
So I am at school recording my video, so there are announcements, but we'll get back to it.
Please report to the media center at 12:15.
So as I was saying, my domain for all real functions goes from negative infinity to infinity, and your range depends on the problem, but there's going to be some number that it approaches but never touches. Okay, next thing we should be able to recognize, tell whether each function represents exponential growth or exponential decay. So the first way that you can figure this out is, of course, to graph it in Desmos. If it's going up, you're going to say growth. If it's going down, you're going to say decay. However, I'm going to show you a shortcut to figure that out. If your base, so here, 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 here. So your base is the number that's attached to the x for the exponent. So if this number is bigger than 1, it's going to be growth. So 2.5 is bigger than 1, so that's growth. And 3/2 is 1.5, which is bigger than 1, so that's growth. If the number is between 0 and 1, then it's going to be decay. So 2 options that you have here. You definitely can graph it in Desmos. You would type each one in. If it's going up, you say growth. If it's going down, you say decay. However, just some things to save you some time. If your base is bigger than 1, it's going to be growth. So if the base is bigger than 1, it's growth. And if your base is between 0 and 1, then it's going to be decay. Keep in mind, we're only going to be working with the positive numbers for this. Okay. Now let's talk about transformations. Our transformations for these are the same as other transformations that we've done this semester. So our transformations are absolutely the same. We can verify that just by typing these into Desmos. And once we graph them in Desmos, it's going to give us the exact same thing that we've been studying earlier in the semester. So let me highlight this one. This is going to be our parent graph. And the first one wants to know what happens from our parent graph to 2 to the x minus 5 power. And we'll need to put that in parentheses. Okay, there we go. So this first one is asking us what's happening from the red to the purple. So my parent function is 2 to the x, and then we want to know what happens from that to 2 to the x minus 5. And all of that is the exponent. So hopefully you do notice that my whole function moved right 5 spaces. So for number 1, it moved right 5 spaces. Again, if we compare this to other functions that we studied this semester, same thing. Whether it was quadratic or cubic or any other function that we've been studying, it still would have moved right 5 spaces. So that's the one that's the opposite of what you think. Now let's see what takes. Let's take a look at number 2. So we're going to add a negative in the front here. This is going to be 2 to just the x power. So we'll get rid of this. And then on the outside, we're going to plus 8. A couple of things happen with this. Hopefully you remember the negative in the front is going to reflect it. And then this plus 8 on the outside moves it up 8 spaces. So number 2 is a reflection across the x-axis. And the plus 8 moves the whole function up 8 spaces. So for number 2, it's a reflection across the x-axis, and it moved up 8 spaces. So reflects across the x-axis, and it goes up 8 spaces. And the last one that we'll take a look at and see what happens. 2 to the x plus 3, and then we're going to subtract 1. Okay. Now we're looking from the red to the purple here. So this one moved left 3, down 1. So this one moved left 3, down 1. So these transformations are no different than what we've been doing kind of earlier in the semester with different kind of functions. If you have a number in the exponent, it's going to move it left or right. If you have a number on the outside, it's going to move it up or down. And if you have a negative in the front, it's going to reflect it. So questions that I can ask you to create functions given certain characteristics, and that's something that you should be able to do.